Alright, in this video we're going to have a look at integration of trig functions, but ones that are a little bit more technical where we have to manipulate first using trig identities and our compound or our double angle formulae. Then we get it into a form that we can either refer to our derivative table or that we can apply one of the rules that we've learned. Now let's first just have a look at these trig identities and compound or double angle formulae. Some of these identities you've covered in core maths and in AP in previous years. Some of the compound and double angle formulae are covered in grade 12 core maths. So for the moment, I want you to be able to identify and use these different identities and formulae, but you will actually go through the proofs of where they come from in core maths. So I don't want that to be our focus now. You will learn where they come from. But I want us to be able to use them. Alright, so let's go through some of our identities that we did last year, that you did in grade 11. Okay, they're all your squared identities. And then remember that they can be arranged. So for example, if I've got 1 plus tan squared of an angle is sec squared of an angle, then tan squared of an angle will be sec squared of an angle minus 1. So you need to remember they can be rearranged. Now here's the compound angle formulae which we're introduced to in grade 11 when you started doing trig for AP. But you haven't done the proofs, and those are the ones that you're going to do in core maths. Just bearing in mind, this means that if I've got sine of an angle, let's take the plus first, another angle. It's the same as sine of the first angle times cos of the second angle plus cos of the first angle times sine of the second angle. Changes if you've got minus. And similarly for cos as well. Now we can adapt these formulae. Now if you have a look here, for example, if we're going to add these together, and that's actually where these adaptations come from, then you work with sine of an angle times cos of an angle. And this is often useful when we're dealing with integrating a function, a trig function, where the angles are different. Right, and it actually comes from just adding the two functions together, which we can look at a little bit further during a tutorial class or if you have a request. From our compound angle formulae, we get double angle formulae. That's just if I've got sine a plus a, which is the same as sine 2a. Bearing in mind, this is going to allow you to take apart double angles or to go from right to left to get to something like on the left-hand side, which might be easier to integrate. Bearing in mind, these last two are often rearranged to get the squared trig function as the subject of the formula, which is very helpful in integration. Some of these are on your information sheet that you get in the exam, some aren't. So you need to go and check what's there and what's not there and make sure that you know these. It's very important. Alright, so let's have a look at some examples. So if we go and have a look at this first example, the integral of tan squared x. Whenever you've got a trig function that you're integrating, your first line of call is to go check your derivative table. So I'm actually going to pop it over here. You check your derivative table, and you see in that derivative column, do you see a tan squared of an angle? You don't. Okay, so we can't go straight to the table. Next line of call is, does it maybe fit one of the rules we've learned? For example, when we had to see the derivative times by a composite function. Not really, because we might have it has a power function, but we don't have a derivative. So because of that, we know, so let me just flip this table away. Because of that, we know that we're going to have to probably use one of our identities. So we go and we have a look. Is there an identity that has tan squared of an angle? Yeah, there we go. 1 plus tan squared of an angle is sec squared of an angle. So I can rewrite that in terms of tan squared of an angle. So let's do that. So I'm going to rewrite tan squared of x as, so I'm still integrating, sec squared x minus 1. Take note of your notation. Don't forget your dx, don't forget your brackets. Now the reason why I could do that, and let's just make a note, is because of the identity that says 1 plus tan squared of an angle is equal to sec squared of an angle. Therefore, if I rearrange it, tan squared of an angle is equal to sec squared of an angle minus 1. So that's where we could rewrite it. Now we're dealing with something that's going to be easier to integrate, bearing in mind that we can split an integral over a minus. So this is the same as integrating sec squared x, don't forget the dx, minus the integral of 1 dx. Now this is a lot easier to integrate if we look at our table. Let me pop my table back here. If I look at my derivative column, I see a sec squared x. The function that I want, the integral of sec squared x, will be tan x. So the integral of sec squared x is tan x. Then I've got a minus, and the integral of 1 is just x. And then I add my constant of integration. All right, let's have a look at another example. If I look at this example here, I might think, okay, well, could I split it and find the integral of cos squared x and the integral of sine squared x? Well, let's have a look at our table. Do I see a cos squared x or a sine squared x here? I don't. So I can't directly go to my table. Then I think, okay, well, could it be a rule? Could I have a power function and its derivative? But I don't see its derivative being multiplied. So my next line of call is to look at my identities. So let's go and see if we can spot anything that could help us. A cos squared x minus a sine squared x. Can't see anything there. Let's check the others. Ah, there we go. Double angle formulae. There's a cos squared of an angle minus sine squared of an angle, and that's equal to cos of 2 times the angle. So that's the one I'm going to use. All right. So instead of integrating this, it's the same as the integral of cos of 2 times my angle, which is x. So just when you're studying, you want to go back and check. We got this from the identity that says cos squared of an angle minus sine squared of an angle is equal to cos of 2 times that angle. Now we're working with something we can integrate, because this is a trig function. It's a composite trig function where the inner function is linear. So remember, with those, I'm going to look at what is the integral of cos 2x? Well, it's sine 2x. But don't forget the half in front, because when we differentiate and go backwards, then because the 2 comes out, we've got something to cancel with. And add your constant of integration. All right, let's look at another example. Okay, in this example, I have a look. I've got sine 4x times by cos 4x. Now, a brief look at the table will show you that there's nothing like this, exactly like that in the table. So you could think, maybe it could be the case where I've got my composite function times by derivative. However, the problem is this 4x. Okay, so we can't go any further. We don't have a perfect composite function times by its derivative, so we can't use that rule directly. However, what we do have is we've got a identity that has sine of an angle times cos of an angle, and that's what we're going to use. So let's go back and just check our angles here. I'm looking for sine of an angle times by cos of an angle. There we go. There's my sine of an angle times by cos of an angle. I can rearrange it, dividing both sides by 2. So this becomes a half sine 2a, or sine 2a over 2 is equal to sine of an angle times cos of an angle. So let's use that. Make our life a lot easier. So it's the same as integrating a half sine. Remember, it's 2 times the angle, and in this case, the angle is 4x. Right, so remember that this comes from that particular rule that says 2 sine of an angle times by cos of an angle is equal to sine of 2 times that angle. Remember, we rearrange it, so sine of an angle times by cos of an angle is equal to half sine 2 times that angle. So that's my identity. I've just divided both sides by 2 to get that. So my angle in this case is 4x. So when I use my identity, I've got to have 2 times that particular angle. Now this becomes something that is much easier to integrate. Take out your constant, and you're finding the integral of sine 2 times 4x is 8x. Now this is just a trig function where it's composite and the inner one is linear, so we can use our rule, but almost, because remember in your table, let's just pop your table back here. In your table, I can only integrate a negative sine x, so I want to create that. So let's do that. So I'm actually going to create a negative, so I want a negative inside, so I've got to pop a negative outside. Alright, so I'm going to integrate. The integral of negative sine of an angle is cos of an angle, but because this is linear, remember I've got to take out 1 over the coefficient, cos of an angle. Okay, then pretty it up in your last step, that becomes negative 1 over 16 cos 8x plus c. Right, let's go on to our next example. Right, in this example, I'm looking at sine squared x. A brief look at your table will tell you you don't see sine squared x. However, we do have an identity where we can rewrite sine squared x. Let's go back and have a look at what that might be. Have a look here. That's where these guys come in handy. I can rewrite sine squared of an angle as a half minus a half cos of 2 times that angle. So that's what I'm going to use there. Right, so I'm going to rewrite sine squared of my angle, and I'm integrating a half minus a half cos of 2 times my angle with respect to x, because of this identity that says sine squared of an angle is equal to a half minus a half cos of 2 times that angle. Now I can split my integral, so I'm integrating a half minus the integral of the second term, and I'm going to take my constant out immediately. A half integral cos 2x dx. Well, the integral of a half is just a half x minus, there's my half that's already there. Here's a composite function where the inner function is linear, so I times by a half, so that's where I get another a half from. The integral of cos 2x is sine 2x. And I now add my constant of integration. My last step is I want to pretty it up a little bit, tie up any loose ends, multiply what needs to be multiplied, so that's a quarter sine 2x plus c. Right, let's look at 2 more examples. These ones are a little bit longer. Let's have a look at this example here. Alright, so here I'm finding the integral of a quarter cos squared x plus sine 3x. Now there's nothing that looks like that in any of my identities. But there's a plus, so I can split it up and work separately. So this is the integral of a quarter cos squared x. I can immediately take out the quarter. So I'm integrating cos squared x with respect to x plus the integral of sine 3x with respect to x. Cool. Now again, you should be starting to identify that I don't have a cos squared x, but I do have a nice identity with a cos squared x. So let's go back there. There you go. Cos squared of an angle I can rewrite as that. So let's do that. Right. So I'm going to rewrite that. There's my quarter. I'm integrating a half plus a half cos 2x with respect to x. Then I'm going to look at the integral of sine 3x. Now we know we can only integrate negative sine 3x, so I introduce a minus outside and a minus inside to make that integrable. I think that's a word. So we can integrate it. So this one, just to make a note here, I got that from the identity that says cos squared of an angle is equal to half plus a half cos of 2 times that angle. Alright, so this is where it's getting long, but don't be alarmed, long is okay. We're going to split up the integral here. So I've got a quarter, and I'm going to integrate a half. Now I'm just distributing that quarter in to the other one. So I've also got plus a quarter. Now notice this, I'm integrating a half cos 2x, I can take the half out. So I take that half out and I'm integrating cos 2x with respect to x. And this I can integrate straight away. I put down my minus. And the integral of negative sine 3x is just 1 over 3 cos 3x. And because I've integrated something, I've got to put a constant of integration, even though I haven't integrated this whole story yet. All right. So I've got a quarter, and the integral of a half dx is a half x. So a quarter times a half x gives me an eighth x. Go straight there. Plus a quarter times a half, there gives me an eighth. And then the integral of cos 2x is a half sine 2x. And then I minus the other story that I already integrated. Now remember to wrap up loose ends, pretty things up a little bit. 1/8 x plus 1 over 16, because that's an eighth times a half, sine 2x minus 1 over 3 cos 3x plus c. Alright, last example. In this example, we see that we've got sine 3x times by 2x, sine 2x. Now, these angles are different, so we can't just go to most of our more straightforward identities. So actually, let's write that down so that you remember it when you're studying. The angles are different. So we can't use most of the, I'm going to put straightforward because these are kind of the ones that we could see quite easily that we've been using. Most of the straightforward identities. So my hint to you, is then we're going to go to compound angle formulae. Because these ones allow for angles of different sizes. So let's do that. I'm going to go down here, we've got a bit more space. Let's go see if we've got a compound angle formula that's got sine of an angle times by sine of a different angle. Here we go. Sine of an angle times by sine of a different angle is that story there. So that's what I'm going to change it to. Notice A is my first angle, B is my second angle. So let's go down and do that. Right, so according to that, I'm now finding the integral, and it says I've got a half, open brackets, cos of the first angle minus the second angle, minus cos of the first angle plus the second angle with respect to x. So that's what that identity says. Now I can simplify this, take out the half, and I'm integrating cos of 3x minus 2x is x, minus cos of 3x plus 2x is 5x. With respect to x, please pay attention to your notation. These brackets need to be here because you're integrating the whole thing. The dx needs to be there. Now we can split this integral up, so it's half, and I'm integrating cos x with respect to x, distribute that half in, and I'm integrating cos 5x with respect to x. Now look how easy this integral is becoming. It started out quite tricky. Now it's very easy because I know that the integral of cos x is sine x. So I've got a half sine x minus a half. The integral of cos 5x is 1 over 5 sine 5x. And I add my constant of integration and pretty it up a little bit. So that's minus 1 over 10 sine 5x plus c. And just for when you're studying, in case you're wondering again where we got this from, let me just put it down here where we have some space. Got that from the identity that says sine of an angle times by cos of an angle is equal to half cos of the first angle minus the second angle minus cos of the first angle plus the second angle. Right, so now take a breath, relax. You need to just know your identities, be able to identify them, and after seeing that the table doesn't work, your other previous methods don't work, that you bring in one of those identities or formulae.